So our first speaker is Govind Menon from Brown University and member this year, right?
Yeah.
I mean, like I was just wondering if it's only one semester or the full year. It's a full year. And he will talk about the geometry of deep learning.
Okay.
Please.
So it's first of all, I just have to say it's a tremendous pleasure to be back here. So this is a problem that actually began 6 years ago. Camilo may not recall this.
I recall.
But, oh, you recall? Okay, in Camilo's office.
With Nadav, definitely he was.
With Nadav. So I kind of want to tell you, so it was kind of a side project at the time, and now it's kind of taken over my life. And so I just want to kind of tell you why. So it's work with a bunch of co-authors. In particular, Nadav was a postdoc over here with Sanjeev Arora. And so I really have to kind of acknowledge, provide, thanks Sanjeev and Nadav for getting me started in this. So what I really want to show you is to kind of give you a flavor for what I think is interesting mathematics in deep learning. And what I'm really just going to do is to focus on kind of proving some theorems for a phenomenological model of deep learning, which was introduced by Arora, Cohen and Hazan in 2017. And the kind of punchline, really, I just want to tell you up front, is that it's this weird structure called a completely integral gradient flow, which very few people know about, but thanks to kind of years of work with Percy Dave, I'm kind of familiar with it. And so sometimes, when you get a solvable system, it's just rare and beautiful. And I kind of want to show you that. At the end, it'll be clear why it's solvable, but I'd like to show you that. And I think once it kind of gives you a sense of kind of how to think about the true, let's say, deep learning problem. And there's a companion paper I wrote, which is on the archive, which is in press, which is basically supposed to be a readable introduction to this world. So first of all, what is deep learning? This is the only place where something nonlinear is going to make an appearance till the end of the talk. But the way you want to think about it as a mathematician is it's a function machine. So it's a way of making functions. And you're making functions between, let's say, two different Euclidean spaces. And the way you make the function is by composing a collection of functions. So the deep refers to the size of this index n. So you want to have many, many layers in here. And so that's the n over there. And the way you make these functions is through a collection of affine shifts combined with a nonlinear transformation. So you kind of, you want to think about a collection of vectors, and you're just applying this nonlinearity entry by entry. Okay, so a typical example, so this is called the ReLU network in the deep learning world. It would be called the Khrushchev entropy in kind of the PDE world, but it's really just the maximum function. So that's a kind of natural way of thinking about it. So one way you want to think about deep learning in terms of, whenever you see these neural networks talk with kind of lots of data and kind of it's important because it's solving problems of the world, somehow I would say a kind of complementary picture is that the way you want to think about what neural networks are doing is it's basically a way of making bump functions. It's a very concrete way of making bound functions. And in some sense, the point of my talk is really going to be that. There's somehow something deeply traditional mathematics in the background. So the way I've written it out, it's really like I give you a bunch of parameters, you feed it through the system, you make a function. But actually in practice, what happens is that the parameters of each affine map are determined from the data. Okay, and so you want to imagine like an image of something high dimensional. And so our goal is to understand the process by which parameters are determined. So this is in some sense one of the central mysteries in the area. These parameters are determined by a gradient flow. And so what we will really do is actually look at this gradient flow with some care in the simplest setting. Okay, so what Arora, Cohen, and Hazan did is said like, okay, this is a complicated process. So let's just focus on the simplest problem within this class, which is to consider training dynamics for how you make linear functions. So I'll fix the dimension of the spaces, input out spaces to be exactly the same, keep things simple. So I'm making a linear function. So it's really just parameterized by a matrix. And so this talk is really about how we make linear functions. And so we want to make a linear function that's best fit to data. And the way we're going to make this linear function by fitting it to data is we're going to minimize a loss function. I'll give you an example of this nature using a gradient flow. Okay, and the loss function is built from the data, typically just a quadratic function. Okay, so what does the DLN have like that kind of corresponds to deep learning? What it really has is depth. So you're over-parametrizing. And I think one of the points of my talk is there are no approximations anywhere. It's going to be a collection of exact formulas. There are kind of like a whole bunch of papers like, D going to infinity limit, et cetera, et cetera. I don't care about that. That's an easier problem. I really just want to kind of give you exact results without any approximation. So what's going on over here is that I'm making a function through composition of linear functions, each of which is given by a matrix. So at the end, I've got a matrix and it's written out as a collection, as a product of a bunch of matrices. So it's really, that's the level of the problem. And so that's the number of entries that I've got in my matrix. And that's the number of parameters that I have. So we've kind of, this is the kind of key piece of this model. So the DLN picks up over-parameterization and it's going to become gradient dynamics. Okay, so what are the gradient dynamics? So we've got, for a gradient flow, you need a parameter space, you need a Riemannian geometry on it, et cetera, et cetera. So all super simple here. A parameter space is a collection of matrices. Okay, so I'm going to write out the matrices in that way. So it's the inverse ordering, just because we're composing functions. So the bold W refers to this collection of matrices. And I've got an observable, so I'm going to call it an observable. So it's the function I'm making from the parameter. And what I'm really going to do is to make, study a gradient flow of this nature, so just a Euclidean gradient flow. And the over-parameterization comes in over there. So the geometry of kind of this over-parameterization is going to play a role in what we do.
E is a loss function.
Yeah, so let me give you an example of an E, and let me give you an example of a machine learning task. Okay, so here's an example of learning with partial data. So this is a problem that Gandes and Co have kind of studied in great detail. So it's a problem called matrix completion. Okay, so the matrix completion problem is that I give you certain entries in a matrix, corresponds to Netflix. User has observed or recommended the system. So you've kind of a user has seen a certain number of movies, but they haven't seen everything. So you kind of have some partial data on what the user wants, and you try to fill in the rest. So the way we kind of want to complete this matrix is that we're going to introduce a cost function that penalizes how far away you are from the diagonal entries. And then you solve the gradient flow. And what you get in the limit is your solution. Does that answer your question, Charles?
Yeah.
Okay. So when I first saw this, I was like, this is some sort of joke. I mean, we've known everything about gradient flows since the 1930s, 1940s. There are all these results that tell us convergence of gradient flows. What could possibly be the issue? So in some sense, it turns out that when you go back and you look at the classical criteria, so like, what do you like about a gradient flow? One of the things we'd like to have is a Morse decomposition. So you say that I'm doing gradient descent of a Morse function, and I can break down the kind of attractor of my system with, collection of critical points separated, connected by stable and unstable manifolds. Well, it turns out this is not a Morse function. It's not a Morse function because of the over-parameterization. It's very degenerate. And so that's kind of the issue, actually. So it's this gradient flow, and you look at it as a dynamicist, you're like, it's just a gradient flow, but it's kind of on the threshold of what we know exactly because of these issues that you don't have coercivity of your energy function. So this is an energy function with a gigantic subset of zeros. An entire affine space consists of zeros. And, so this is kind of a bit embarrassing, but this is the status of the theory. So here's an open problem, just for 2x2 matrices. So I take the matrix completion problem that I just showed you. I look at the zero energy set. So this is an affine space consisting of matrices of that nature. And then you run numerics on this. And within this affine space, so this is kind of the zero energy set of our energies. So within this affine space, there are two rank 1 curves. So curves of matrices which are rank 1. And randomly chosen initial conditions are observed to converge to these rank 1 to these affine, so it's a numerical experiment, but I have no idea how to prove this. So I'll make this even simpler a little bit later in the talk. It's going to be and even so, in principle over here, I'm solving my gradient flow for all of these matrices. I'll give you a simpler version where the problem is still open. So this is kind of one of the interesting aspects of the problem. There are kind of these elementary problems that one can state, like just simple analysis problems, and somehow they're still not solved.
So yeah, can you be more precise about that? So you mean yes?
Yeah, I'll give it to you and just hold the question. I'll come back to it. Yeah, I'll come back to this example. I just want to demonstrate somehow just something concrete and interesting. Okay, so let me tell you about some of the stuff that we can prove and to kind of give you a flavor of the theorems. So first of all, what does the gradient flow actually look like? So this was a collection of matrices. So that's just an abstract equation. But what it really works out to, when you apply the chain rule, is that you get a collection of n matrix valued equations of this sort. Okay, so it corresponds to overparameterization. It's really just a simple consequence of the chain rule. And this equation is going to have, we're just going to fool around with it and kind of prove some properties. But in some ways, you want to kind of think about this equation, the fact that we've got the chain rule over here as being central to all of deep learning. So deep learning works with an effective computation of chain rule using what's called the backpropagation algorithm. And so the form of the chain rule over here that you've got kind of these factors on the left, those factors on the right, that really reflects the nature of backpropagation. So geometrically, the way you want to think about this is that I've got a space downstairs. So this is where my observable lives. The energy depends only on the observable. So the energy is constant on fibers. Okay, so the fibers are this algebraic, the solution to this particular collection of polynomial equations. So I give you X. There's a collection of matrices that solves this equation. And so that's my fiber over there. So the gradients are orthogonal to the fibers. So this is kind of very easy to see. And so one of the things that kind of is important, the kind of general consequence of the type of gradient flows that are showing up in deep learning is that they are very thin. The gradient goes only in certain directions. So the fibers have, in this case, dimension n-1 d squared. So n-1 matrices times d squared. And so you're actually going only in d squared direction. So the kind of the space of gradients is actually somehow very thin. And there are kind of a bunch of consequences related to that. So one of the consequences is actually this sort of surprising feature. So when you have a gradient flow, you don't expect gradient flow to have conservation laws, integrals of motion. But it turns out that this particular gradient flow has many, many integrals of motion. So the integrals of motion are actually a collection of symmetric matrices. So when we really do it, you have to go to Hermitian matrices, but let's stick with real matrices up here. So I've got a collection of symmetric matrices prescribed by this particular algebraic equation. And the way Arora, Cohen, and Hazan, so the theorem of Arora, Cohen, and Hazan is that if you consider the gradient flow, then the gradient flow conserves all of these matrices. Okay, so what's interesting about this in some sense is that, first of all, the type of loss function doesn't matter. It's really just a statement about the geometry of the vector fields. And that's a bit strange. I mean, I just give you an equation and say like, okay, it's got these conservation laws. And it turns out that the theorem is actually, it's a one-line proof, right? So what you do is like, you take this equation, you multiply on the left, you multiply on the right. So you take, you've got a collection of these guys. P denotes your index down the network. And so you just kind of multiply on the left, multiply on the right, take your transpose, and you check, and it just works. Okay, yeah.
Would only expect this in the completely linear situation, but if I add nonlinearities.
So let's hold it. Let's treat the linear problem. So just think about this as a math problem on gradient flows. I'll get back to the nonlinear stuff at the end of the talk. So I think it's just like it's just nice to kind of see what the structure is of this problem, and then kind of understand that fully, and then kind of move towards nonlinear. I just want to the point of the talk really is kind of understanding the geometry behind the type of gradient flows we're seeing, getting kind of good solvable example, and then kind of building our intuition based on that. There will be interesting theorems, please just hold on for a second. Okay, so the interesting thing about these conservation laws is that, these are quadratic equations. quadratic matrix valued equations. And, for various reasons, I'm going to kind of draw them as these conic sections in the space of matrices. And in particular, there's a particular case where all of these conservation laws are zero. So the G's are all zero. So depending upon what the G's are, you get these kind of generalized hyperbolas, let's say, in the space of matrices. And there's a critical one that separates these guys. Okay. So let's get our hands dirty. So, one of the things I learned from Percy Dent is if you can understand stuff for 2 by 2 matrices, you can understand a lot. So let's look at those equations. I've got 2 matrices. So I take depth 2 and dimension 2. So I'm just looking at that algebraic equation. So that's really equivalent to 3 equations in R8. And I take these 3 equations, those are 3 equations of DLN, and you add those 3 equations, and now you see that, like your computational law, somehow there's something magical that shows up. Suddenly you see the Simon's Cohen there. So I think it's rather appropriate that Sanjeev and Nadav showed it to us in Camilo's office. So 6 years later, here's the connection. There's the Simon's Cohen showing up in this. And so I'd seen the Simon's Cohen before. I was like, wait, this is weird. Why exactly is the Simon's Cohen showing up in deep learning? So let me make a sketch of that so you can kind of play around with the parameters over here, try to understand these quadratics a little bit later. So let me focus on this particular manifold. So there's a bunch of theorems that we will prove which are related to the flow on that variety, and that variety is foliated by leaves of matrices of rank. So I'm going to focus on the full rank case. And so that's the full rank collection. And so it turns out that, you can do a very simple dimension counting argument, count the number of equations over here, count the number of variables that you have. And you see that the dimension of this balanced manifold, there's d squared, which corresponds to a point downstairs. And then there's actually a group action. So one of the ways you want to think about this manifold, this is our invariant manifold in our dynamical system. And this invariant manifold is sliced by these orbits, so group orbits associated to the orthogonal group. So it turns out that, in fact, actually you can determine, so, it's one of these, so you've got an invariant manifold in a dynamical system. You want to understand what are the equations on the invariant manifold. And Arora, Cohen and Hazan observed, so this is really a nice calculation. So they observed that you do, if you've got your dynamical system living upstairs, but then you take the observable downstairs, which is the product of these matrices, and voila, it ends up solving a closed equation of its own, which is very, very explicit. So a couple of years later, so actually this appeared in print a bit later, but the theorem comes before. So there's actually a collection of 2 different theorems. Rahut's group and kind of Michael Westingenberg, so this collection, this group of 4 authors, basically recognize that this equation that you're seeing is actually equivalent to a Riemannian gradient flow on the space of matrices downstairs, and they could write out the metric in a slightly cumbersome manner. And then my student Tianmin and I basically kind of found the natural geometry that goes with this. So it turns out that you've got this flow upstairs, but the flow upstairs, so you've got a Euclidean gradient flow upstairs living on this critical manifold, and it projects downstairs onto a Riemannian gradient flow, and you can actually, the geometry that you get downstairs is the natural geometry that comes from the Riemannian submersion. So the core of this theorem is actually a very explicit computation of an orthonormal basis for the tangent space. And this computation is rather interesting because it kind of shows you a coupling along the network, which you don't quite expect. And you kind of have to use kind of block Jacobi matrices to do it. So it's a beautiful, beautiful calculation done by my student. And that's when you kind of begin to see the flavor of integrability. You're dealing with tridiagonal matrices, there's kind of accidents you don't quite accept. And somehow you go back and you're like, okay, there's a natural geometric reason for this. So to go back to the kind of open problem that I began with, so here's a kind of, I've cut it down in some sense to the simplest form. It's really an ODE problem. I feel I should have a kind of good concrete ODE problem or sour PDE problem in an analysis seminar. So here's the problem, and I still don't know the answer to it. So I've got, d is equal to 2. So this is a 4-dimensional system. Take a simple quadratic energy, show that small initial conditions actually converge to this rank 1 manifold. And I don't know the answer to this. So there's some estimate that's required, and I don't know what this estimate is. So it turns out that this low rank phenomena is actually super important in this business. So in fact, these are kind of cute analysis, or kind of like, the basic analysis problems that we actually need for large numerical simulations that basically demonstrate this phenomena and relate to kind of, how you're kind of coding your information using deep learning. So I think it's not just a kind of problem. It's an elementary and interesting problem, but I think it actually captures something much more. Yeah.
And this, you see it independently of big N.
Independently of big N, yeah. So we tested it. So we tested it for like.
And of course.
You just it's just a 2x2 matrix flow. It's it's something like you try stuff like look at how the determinant changes or something like that. But and I know that this is even a gradient flow. But the metric is a little bit complicated, but somehow there's a part of it which is
So will each initial condition converge to one point on that, or start?
So you find what you find is kind of clusters over here, and there's a kind of distribution of where it's clustering, which is dependent upon the depth.
But each initial condition will give you one point on there.
Exactly. Yeah.
And I think
really just
I mean, it's real analytics, so it's going to follow from Voyagevich's work, right?
So Loya-Schwitz tells you that it's converging to something. It's not telling you that it's converging.
No, I mean the fact that it's unique. That's what I'm saying.
That's what I was asking.
Okay. Oh, yes. So that's completely
Yeah.
correct. So that's exactly it. So that's so like so Westickenberg's or Rahut and co. They basically use Loya-Schwitz to prove that you've got convergence under certain bounds. So you actually just need to get an a priori bound.
Or something like that, right?
Yeah. It's basically because it's analytic, it's quadratic energy, so it works just fine. I have to say that still bothers me because Loya-Schwitz is in some sense a high-powered theorem because it's kind of using logic. There's no element. So it's like this. Just I feel like they should be simpler. Anyway, so I think this is a kind of analysis problem that is.
So you say it's open because there are other critical points that you're.
No, it's open because I don't know how to prove this. I haven't proved. We don't have a proof that it goes to. So Loya-Schwitz is telling you that it's converging to something. It's not. It's converging. Yeah, but this entire space is critical points. So this is a 4-dimensional space.
The thing that you were
Right.
Oh,
so I
okay.
actually got. Yeah.
Okay, I got you.
So it's really kind of. It's not. Yes.
Those are all critical, but for some reasons you're only converging to the.
That's exactly it. Okay, great. That's exactly it. So that's exactly the issue here. And that's kind of a general issue in all of deep learning. You often have shallow energy basins. You've got lots of critical points, and somehow you go into critical points which actually have some special properties. So I'll give you a kind of framework for thinking about this, but in some sense, that's the point. Absolutely.
And just one question.
Yeah.
So those special properties are usually interpreted in some way.
So it's typically low rank phenomena. It's typically low rank phenomena. So somehow you're picking up sparsity. So that's
Is that somehow good for your neural network?
Yeah, I'll get to that right now. So I'll tell you exactly in what sense it's good for the neural network right now. Yeah, so it's
Did you also run experiments where the hidden dimensions are larger? Where you don't.
so here, yeah, absolutely. So so this is a phenomena that you see. The phenomena is like somehow we're just picking small initial conditions and letting it go. And the depth over here, I can choose to be whatever. So I don't care about this. Yeah, so that's actually a huge point of the DLN. You don't have to make any assumptions about the dimension of the system or the depth. All the theorems are kind of, fixed N, fixed D, you get the theorem. So there's a kind of solvability in there that is kind of important. Okay, so
I'll ask a little
Yeah.
question. I've heard that when you discretize the time, you can get different answers.
So absolutely, right? So in some ways, like, so if you actually do kind of deep learning, people do discrete time.
Yes.
And it's stochastic gradient descent, where you're not computing your gradients in all
And you
directions.
still get the same?
But, well, we are doing numerics with discretized time. So, there's a sense in which you're picking up stuff. But I think the viewpoint I would say is really, you want to get the gradient flows right. just because you actually, if you're going to prove any sort of theorems on convergence for the actual numerics, this is your benchmark. And in some sense, the issue over here is that the benchmark is appears to be so simple over here, linear functions, 2 by 2, and like it's more like this is the minimum complexity, and like what are we missing over here? Okay, so I actually kind of want to focus now on kind of the emergence in some sense of the Simon's cone and these generalized structures. And I kind of want to show you where it's coming from and to kind of reflect a little bit on kind of a surprise in there. So it turns out that I've shown you the fibers, but the fibers are actually group orbits, so that's relatively easy to check. And what's really going on is that, you know, I mean, we are really working with the product of matrices. So this is in some sense really an algebraic geometry problem. And one of the things that you observe is that if you smuggle in a matrix, an invertible matrix in this particular form along any index down there, then you're going to stay on the fiber. So there's a group acting on the fiber, and it's keeping, you know, so the group acting linearly on the fiber. So the group GLD n minus 1 acts linearly on this vector space, and it kind of keeps you on the fiber. On the other hand, the conservation laws for the gradient flow are somehow related to a subgroup symmetry. So where exactly does this come from and why? So this really bothered me for like 2 years. And it bothered me because, you know, to cut to the punchline, somehow I had a very clean geometric picture of what's going on in the DLN. And I wanted to take that geometric picture and take it to the kind of nonlinear networks. And I couldn't take it to the nonlinear networks because I just couldn't understand where this reduction in symmetry was coming from. And so that we figured out earlier this year. So this is a theorem with Kathryn Lindsey at Boston College. And the theorem is a very straightforward theorem. So it's, you know, so this is called the regularizer in the machine learning community. So take the L2 norm. And the theorem is very straightforward. This says that the regularizer of the L2 norm restricted to the fiber is this critical orbit that I showed you. Okay, and in fact, the integrals, the GNs that we had earlier, are obtained from the moment map associated to this regularizer. Okay, so this is really a theorem in complex matrices, and it's really not a theorem that I was familiar with at all. But let me give you a picture of what this theorem actually means. So in some sense, what's going on is that our parameter space has two complementary foliations. So the first one I showed you is the foliation by the hyperbolas, by the MGs. And there's a complementary foliation given by the constant G curves. And so in some sense, you've got one mapping which is bringing you down over here to the X, and another one which is taking you to the G's. And what I'm really telling you is that this mapping has a particular structure which is related to minimization of the energy on the group orbit. Okay. So let me explain to you what the theorem means in terms of practice. So the theorem is that this balancedness provides model reduction. Okay. So what that means is that you're sitting on this fiber, and I'm looking at the collection of matrices, or, you know, a bunch of these matrices whose product will be equal to a given matrix X. And sitting on this kind of fiber is this critical orbit. So this kind of corresponded to a slice of this kind of generalized Simon's cone. And let me pick, you know, one point. I'll call that the center. And if that's the singular value decomposition of X, then you know, take the nth root of the singular values. And the center is actually, in some sense, the simplest parametric representation of the product. It's like, okay, I give you a collection of matrices, you can compute the product. But if I give you the product and ask you what's the matrices, give me n matrices whose product is equal to this one point, then, you know, this is clearly the simplest way in which you could represent a product in terms of collection of matrices. So this is actually, it's, you know, for people in practice, this is model reduction. It tells you that, you know, when you're regularizing, so I'm thinking of a gradient flow along the fiber, what regularizing is going to do is it's going to give you the simplest possible way of representing your observable. So there's the center, and then you kind of move around from the center according to this OD to the n-1 action. And so this actually is in some sense related to kind of the Yang-Mills seminar of Tom in the following way. So if you look at the collection of matrices, so one kind of natural coordinate description collection of matrices is to write them out with the SVD. And what happens when you're on this critical orbit is that the rotation matrices so if you look at each of these pairs, you see that the right singular vectors of Wn align with the left singular vectors of Wn-1, and so on. So the singular vectors are all kind of aligned, and when you go up, they kind of begin to get twisted up. So it turns out that this is actually the easiest theorem I proved in my life, and it's in a sense not a theorem I proved in my life, because it's really an algebraic geometry theorem. So it turns out that there are two concepts of balancedness. So balancedness, this term had kind of showed up earlier in in control theory, in the study of linear systems. And then it kind of showed up in deep learning, and there's kind of been a bunch of attempts to try and understand where this was coming from. So it's something like this, right? Like when you see conservation laws in dynamical systems, you want to say that the conservation laws are related to a symmetry, to some sort of Noether theorem. And so somehow it turns out that this is where the Noether theorem comes from. And the Kempf-Ness theorem is a theorem that kind of comes from algebraic geometry and fits exactly within this setting. It basically tells us exactly what we wanted to know. So it's kind of, think about it in the following way. So what I'm doing is I'm minimizing the energy on this fiber. And what the Kempf-Ness theorem is telling me is like, you're minimizing your energy in the fiber, it's going to be minimized at this point. The theorem is actually a little bit more subtle than that. What it really does is to classify closed or non-closed orbits. So somehow one of the group actions would be an unclosed orbit. So like this upper axis or that upper axis. And those orbits are not closed. So somehow this was very weird to me. I'd never heard about the Kempf-Ness theorem, but it does exactly what we need. And it does exactly what we need, both in terms of telling us the math structure, but also in telling us in terms of the interpretation. So it turns out that when you go back to where this stuff is used in control theory, it goes back all the way to Kalman in the 1960s. I just want to kind of show you the introduction to the paper of Kalman. So Kalman says that there are two different ways of thinking about dynamical systems. So one is the axiomatic one, where you say like, okay, here's my differential equation, comes from physics, comes from Newton. And then there's another one, which is kind of, let's say, data. So you just say that a linear system is described by input, output, like you've got input and you've got output and you've got the responses. So what Kalman does is kind of, he writes a series of papers where he kind of studies linear systems from within this framework, and he comes up with the notions of controllability and observability. So Kalman's realizability theory somehow in this context is like, okay, you've got an axiomatic definition. So there's your system. The system is prescribed by four matrices. So it's called linear systems theory. So that's the control, and that's the output. So the key fact over here is you can only push in certain directions. You can only measure in certain directions. So you really have only a response. You only have a relationship between the input and the output. And now you record that in a Hankel matrix. So that's a meromorphic function. So it turns out that this meromorphic function is related to your system parameters through group action. Okay. So if I give you the data, then I'm giving you this function. And this is the class of systems which are compatible with the data. So when you're doing model reductions, you've got many, many ways of representing the same data. What you want is the optimal way of representing the data. And so you're really minimizing, so you're trying to figure out kind of what's the best representation over a GLN action. And that's basically what was solved by the Kempf-Ness theorem. So the theorem kind of has kind of, like we can use it in a probabilistic way. So one of the issues in deep learning, so one of there are different frameworks of artificial intelligence. And one of the things that this minimization principle actually tells us is that if you look at Gaussian measures, so if I start out my problem by just saying I'm taking weights at random, and then I condition on the weights being, the product of the weights being a particular matrix, so I have Gaussian measure restricted to this fiber, the statement is that the Gaussian measure is going to be somehow concentrated around the point of minimum. So that's not so hard to see if you kind of look at this function, and we've, I proved a theorem saying that function is minimized on this critical orbit. But there's also a Jacobian factor, and you have to actually compute this Jacobian factor. So explicitly, this is the kind of flavor of the solvability of this problem. So, you can write out this integral as an integral over a group. It's kind of got a flavor of Harishchandra integrals. And so somehow there's a piece of this, we actually have to do these very, very explicit computations. And somehow it kind of, let's say the Kempf-Ness piece, the balancedness piece actually fits rather nicely with the piece where you actually think about this in terms of data. So I see this because there are two statistical frameworks for artificial intelligence, and I got into this thanks to the work of David Mumford. So Mumford, I've known Mumford only in this kind of AI phase, and I wasn't even in AI, but about 15 years ago, I decided to get into it. So I began to teach based upon kind of Mumford's or kind of Grenander's framework. So Grenander's framework for AI basically goes as follows. You say the world is made of random signals. You observe data, and then inference is maximum likelihood. So it's always Bayesian inference. And so the game is to basically construct priors, to construct signals. Then you observe data, and then you have to do an optimization problem. There's another framework. So this is a neural network. So there's also kind of a framework of which is statistical. But somehow the core of this framework is that you've got a function machine neural networks. You've got data, and you build a function based upon these two. Now, that doesn't work. Okay, so one of the big lessons over in kind of, let's say, neural network theory is that this stuff, it's a principled way of thinking of machine learning as science, but it really does not work in practice. It's not competitive as soon as you go into kind of relatively simple tasks like character recognition, which an undergrad can solve. On the other hand, it turns out that when you're looking at deep learning, it is certainly true that you kind of, Mumford's work survives, but kind of the algebraic geometry work survives. So it's really like the Kempf-Ness theorem. I've had this book on my shelf for about 15 years. I've never actually looked at it. I looked at it, I still find it equally intimidating, but somehow it's basically the tools from Kempf-Ness that have actually explained to us how to kind of do model reduction in this problem. So the critical step over here, so Linda Ness was David's student, and kind of it's exactly their theorem that we need to prove this fact.
Did you tell us what that theorem is yet or not?
Oh, the theorem, okay, sorry, I should, so yeah, I didn't quite, okay. So it's a theorem, okay, so it's, okay, so let me write it down. So the general structure of the theorem is something like this. So you're looking at a group, so you have a vector space and a group, and you're looking at, the group must act linearly on the vector space. Okay, so in my setting, the group is going to be, so I'm really doing it for complex matrices. The vector space is MD to the N. And the way, so, this I'm going to write out, so I've got a collection of invertible matrices. So the X is going to become, so X is replaced by W, so it's a collection of these matrices. And the group action over here is G dot X is now replaced by, so it's kind of, let's say, A dot W. And so it's W is mapped to Wn AN minus 1 inverse, AN minus 1, Wn minus 1, AN minus 2 inverse. So you've got a group action which preserves the product. Okay. So what you're really trying to do is you're really working on this. So this is a collection of algebraic equations. That's why I'm working over the complexes. Okay, so now what you do is you look at functionals on this guy. So you have to have, in addition to this, so K is, so it has to be a maximally compact subgroup of this group. So in our case, K is the unitary group. And now the kind of amazing theorem of Kempf-Ness in this context is that if you are minimizing, so it's related to the norms of vectors. So the statement is that if you minimize the squared norm on a fiber, then the squared norm is minimized if and only if the group orbits are closed. And when they are minimized, there will be a unique minimum. Sorry, not a unique minimum. So if you have a critical point, it is going to be a minimum. So in some sense, what's happening is that you get a collection. It's a kind of hidden convexity theorem. It's really beautiful. You've got these functions on these group orbits, and it kind of gives you a class of functions that are replacements for convex functions on this. So it turns out that it's not just the square norm that works, but any kind of pluri-subharmonic function, any strictly pluri-subharmonic function would all be minimized on this orbit. So it's just a high-powered theorem, and it was just right for our needs. But I think it's actually, I think there's something rather deep going on over here in terms of how it fits for us. Yeah.
So just a question in this context. The way that I think about the Kempf-Ness theorem,
Yeah.
that tells you which points are stable, unstable.
Absolutely, right? So somehow, so that's the stuff. So I didn't know about this theorem until 3 months ago. So I've been actually trying to read various geometric invariant theory notes. And so like when we do this, actually we are almost cheating. We've not kind of understood the null code. In some ways, I believe like this must be a kind of textbook exercise for someone who knows algebraic geometry. I don't. But in some sense, that's exactly it. You want to classify the very stable points, and then you kind of want to equip the orbit space with
Right. There should be also a relationship between the GIT quotient where you take
Exactly.
So you take the stable point.
That's exactly my point.
Your reduction.
Yeah.
Okay.
Yeah.
So that's
Exactly. That's exactly what I'm saying.
Okay.
So what I'm saying is that in some sense, what's happening over here is we have this in the background. So there's really, in some sense, it's not. So it's like the problem comes to you from deep learning. Like what you're really doing is you're doing a gradient flow in an algebraic variety. So of course you're going to have solvable structure, but still like the details, the way it comes out is really, really interesting. And in some sense, what happens is that you can, like on my end, what I'm really doing is I'm interpreting these theorems probabilistically. And in some sense, what I'm actually doing is actually looking at the gradient flow quantitatively. And I need to look at it quantitatively, and somehow that gives me, sort of, let's say, a new way of kind of, or not a new way of thinking about these theorems, but let's say new utilization of these theorems, which is kind of exactly right for us. Okay, so yeah, I mean, if you know how to compute this stuff, please let me know. Yeah.
I don't think so.
Well, it's really like, honestly, I look at kind of notes on GIT, and they all begin with this kind of simple 2D example to show you. And they're like, well, this is exactly the same thing. I mean, this is just a matrix version of that. And with hindsight, it's completely clear that this stuff should come out. So in our case, it tells us exactly what we want. It kind of gives us a dynamic decomposition. So I'll show you that in a second. Okay, maybe I may have to. So anyway, yeah. So that's kind of it's still at this point a sort of magic hammer. I don't feel kind of fully comfortable with it. It's not kind of in my skill set, but somehow it's just something that works just right for us. Okay, so somehow what's happened is that actually we can think about training dynamics kind of consisting of two very different dynamical systems. So there's one flow, which is a flow on the fiber. So I'm going to think about this as a fast dynamics where I'm just regularizing. So I'm minimizing this quadratic energy with the condition on the end-to-end matrix. And that drives me down to this optimal representation of the observable in terms of the parameters. You really want to think about this as the optimal representation. So once you've got the optimal representation, you've actually got what I will call the learning flow, which is a gradient dynamical system, which is living on this critical cone and is mapped to a kind of gradient downstairs. So we call this thermodynamics because in some sense, one of the things that we can begin to do is you've got a space upstairs, so a space of microstates. And that's where we think about our noise living in our system. And you can do a bunch of things. So one of the things that we were able to do is to actually form a notion of entropy and then kind of make this, make the kind of microscopic dynamics that go with the entropy precise. So, whenever you're thinking about a notion of entropy, what you have to do is you have to quantify. It's always Boltzmann's formula, log of number of states. You want to quantify the degeneracy. So if I've got an X downstairs, I'm looking at the number of states that can make it, and I'm enumerating them. So I have to compute a volume. And there's an exact formula for the volume. And so this is a theorem that Tianmin proved in his thesis. And it's a statement, it's a determinantal formula. So it's very much like in random matrix theory. The volume of the group orbit is given by a ratio of van der Monde determinants. And so the way you do this is, again, by kind of RMT type techniques, you have to kind of diagonalize the metrics. So everything kind of boils down to computing pullback metrics and then just kind of diagonalizing them. So you're computing metrics on this big space, but somehow it kind of works out rather cleanly, perhaps not surprisingly with hindsight, but you can prove these exact formulas. Let me just kind of maybe not go too far in. So there's stuff that we can do with this. So the stuff that we can do with this is we kind of want to have a notion of equilibration. And so we kind of have, going back to this problem of kind of determining the rank one minimizer. So one of the things you want to do in such problems is to add in small noise and see what happens. And so the way we do that is by going from the loss function to a free energy, doing a gradient flow of the free energy, and contrasting the gradient flow of the free energy with stochastic dynamics upstairs. And so a theorem in the area that we could prove is that if I consider this stochastic differential equation taking place in the parameter space, so that's my gradient flow that I began with. And now what I've done is I'm pushing it with Brownian motion on the cone. So somehow you have to figure out how to construct the Brownian motion on the cone. But it's a natural way of kind of perturbing in a way that is consistent with the geometry of your system. And somehow you can prove in the system that the free energy gradient downstairs corresponds to the stochastic dynamics upstairs. And the background over here, this kind of comes from construction, a new construction of Dyson-Brownian motion, a kind of fundamental object in RMT that Dominic and Jingpeng Wang and I came up with a couple of years ago. Yeah.
Just a question about heuristics.
Yeah.
I mean, this equation is like geometric Brownian motion to me.
It is. That's exactly what it is.
And then so you're adding this stochastic term to gradient descent.
Yeah.
So you're not gonna hit. You don't expect to hit minimum.
Well, actually, that's the point. I added in the noise. Okay, so let me. I forgot. So somehow what I'm doing is I'm adding in noise only in the gauge fields. So it's my noise is jiggling only in the tangential directions, and so that's actually the point of the theorem. Where did it go? Where's the theorem? Yeah. So take a look at the theorem, right? So this is parameter space upstairs. And so in parameter space, it's kind of like, let me make a picture that's straightforward. So my dynamics is now just, so I've kind of got noisy dynamics over here. So the perturbation, the noise is constructed in a way that it's always living over here. And when I do that, what I have downstairs is actually deterministic.
Okay.
Okay. So that's it's a subtle trick. You don't quite expect noise to just kind of cancel out, but you use the kind of null directions to kind of cancel out in some sense the noise downstairs. So I can talk a little bit more after. Yeah.
And maybe you said something, but I missed something. the drift, I guess, this PW.
Yeah. Oh no, that's a projection. So it's really like, it's how you construct noise on the cone. It's like take noise in your ambient space, project the damn thing onto onto the cone. So it's a way of kind of making. If you've got a Riemannian manifold, you want to make Brownian motion on your Riemannian manifold. There's something called the extrinsic construction. You have to kind of project it down onto the manifold. So that's really what happened over here. Okay. So somehow let me just kind of, I've got 10 minutes. Let me just kind of, conclude by kind of telling you why actually what the DLN actually tells you about deep learning. I think it's an interesting problem just because you can solve it and then, one should never minimize that aspect. So somehow I decided, this was about 2-3 years ago, And I decided to kind of actually, just kind of construct a kind of classroom exercise on training dynamics. And so the classroom exercise goes as follows. We think about there's human ways of making functions. So I'm going to sample a random function according to some familiar method. And then I give it to my students because I kind of wanted to see what conclusions are agnostic, independent of architecture, independent of academic fiefdoms. I just want to know, I told the students, try arbitrary networks and see what works best, right? So let's look at how training actually works without any sort of bias. So what I did is I chose kind of stationary Gaussian processes on the circle. So this is a kind of very familiar family of random functions. And it's a simple mechanical Turk experiment where I kind of give it to my class, they do the training, and I see what comes out, right? So here are the functions I gave my students. So these are random functions from kind of different smoothness classes. And then you train them. So these are kind of outputs by one of my students. And let's look at what training does, right? So the yellow over here is the random function. The blue in the background is the neural network's approximation. And what you're seeing over here is snapshots as time goes on. And one of the fascinating features, and you just see this repeatedly whenever you do training dynamics, and it's kind of related to what's called the central mystery in deep learning, where you don't have overfitting. So somehow you've got all of these parameters, but you never kind of, the function that you make is never rougher than what you start out with. So what actually happens when you do this fitting is that the fitting is somehow scale by scale. The blue, as you can see, is kind of becoming rougher and rougher until it kind of fits in just the right way. So for me, what's happening is that you're kind of, this looks very much like renormalization. It is in some ways, I would guess, kind of precisely a renormalization. And the whole reason for kind of wanting this concept of balancedness to have it in such sharp form is that in some sense, Riemannian submersion as a picture of thinking about how dynamics takes place is completely agnostic to neural architecture. It's really like, now my space downstairs is a space of functions, and associated to my function downstairs is just a collection of parameters upstairs, so just manifolds upstairs that make a particular function. So within each of these guys, once you've got a minimization principle that tells you what balancedness is, so there's this kind of minimal subgroup that pops out, you want to classify that by a variational principle. So within these kind of various sets of parameters that make a particular function, there are subsets that kind of actually matter in terms of the training dynamics, and these subsets correspond to optimal codings of this function. And so somehow my picture of deep learning now in infinite dimensions is that there are these two processes. There's one process which is regularization, and there's another process which is learning. Great. And so you kind of, you kind of want to use the Riemannian submersion idea. And kind of there are kind of various reasons for this, but somehow what we expect downstairs is that you've got a gradient flow in a function space, but this gradient flow in the function space is obtained, for various reasons, should have a sub-Riemannian geometry. So this comes back to actually, ways in which Dominic Inauen and I have been thinking about the kind of Nash embedding theorems for a bunch of years. And okay, this is more philosophy than theorem at this point, but it's a picture in terms of how to think about training dynamics. And so, let me stop at this point. In some sense, I think the question, what I really want to show you is that deep learning contains interesting mathematics, kind of unexpected connections between different areas. I think it really comes down to the fact that there are actually three basic questions, three kind of real fundamental mathematical questions that are in play. The first one is really, how do you just make functions? It's a particular recipe for making functions from data. Second one is really, how do you make manifolds from data? Because what's actually happening in parameter space is you're making manifolds. These manifolds are evolving in normal directions. That's what the gradient flows do. And the whole reason for emphasizing thermodynamics, this notion of equilibria, the upstairs, downstairs story, is really to understand what I would call our fundamental limits of computing. What can you actually do in this area? And I kind of leave you with this quote And it's actually a fact that a computer, so this is kind of a combination of the Turing machine and Carnot cycle. So this is from Bennett's work in the 1960s, rewritten in the 1980s, which is that. So anyway, so that's the story on where we are with this problem and with this class of problems. There's a whole bunch of papers I haven't shown you, but I just want to tell you a story in terms of like neat theorems unexpectedly showing up in this area. So I think it's 6 years since the conversation with Sanjeev and Nadav, but I think we have a good story at this point. So thank you very much.
Questions?
Yes.
So when you add a nonlinearity
Yeah.
in your network,
Yeah.
so you still believe in this?
So as I said, like Riemannian submersion is like this notion that you're like the notion of Riemannian submersion is actually agnostic, completely agnostic to the architecture. So one of the things that happens in this area is like, so like there's a sense, let me kind of explain that a little bit more carefully, right? So one of the things that happens in the area is that we are trying to solve kind of problems coming from the computer scientists, right? So they give you a model and they have their framework, which is very much about like, it's like, can you prove like this type of bound or that type of bound, or can you show like this unit is better than that? Like ReLU is better than that unit because like it worked better in practice. So those are kind of real questions, but in some sense, one of the ways I think we need to ask, like one of the ways we need to approach these things is by actually having a framework in which you can address the dynamics. That's the critical point that's missing. So somehow the entire framework, of looking at deep learning is based on statistical learning theory. So the way it's kind of written as, let's say, fundamental mystery of deep learning is like statistical learning theory tells you that you will have overfitting. You don't have overfitting, then you're like, okay, what do I need to do to present overfitting? So when you look carefully, you realize that there's no actual theorems on the convergence of the dynamics. Now, this is not surprising because as you see in a 2x2 example, we don't have theorems. So there's a sense in which proving that the dynamics takes you to something is the mathematical question. So here's a constructed example, not kind of an actual data set, but a constructed example where I pick a random function, I see what training does, and you see very, very clearly that the training dynamics does not give you overfitting. So somehow there's a process, a dynamic process, for which you don't get the overfitting. So I suspect what's really going on is that it's really this infinite dimensional gradient flow with a subtle metric, which comes from Riemannian submersion plus balancedness. That's why getting balancedness right, understanding what balancedness meant.
What did you call balancedness? Sorry.
So balancedness was this, here, let me show it to you. It's somehow this picture. Okay, so I fix my function downstairs. I look at the set of matrices that will make this. So this is a picture in some sense of the solution to this equation. And any one of these matrices, any point on the space is going to give me a representation of my function downstairs. Yes. But it's only somehow this critical subgroup that really matters. And when you look on this critical subgroup, you have the optimal way of reconstructing from the bottom. Okay? And somehow this fits beautifully with geometric invariant theory. So I'm being guided by mathematical beauty over here, right? Like here's this unexpected stuff. So it's somehow stuff that's also kind of natural. So it's kind of like, I don't know, you're making a function by composition. Over here, you're just making a linear function by composition. And somehow when you're making this linear function by composition, what's happening is that your singular vectors are getting aligned. So it's like you have maximal flow of information down the chain. So it's a very clean idea, which you can approach in many different ways for the linear model. And what happens when you think about it for the linear model is like, okay, so here's a stochastic way of thinking about it. You think about, okay, I mean, let me not get too far in, but it's somehow like you're expecting kind of Brownian motion in this critical subgroup to kind of determine the structure of the data. So there's a reason why this picture kind of matters a lot to me because this picture is exactly what I can translate to kind of the nonlinear network. So of course, what you do with the nonlinear thing, you do numerics first with that metric to see that you have this gradient flow. But that's kind of the point. It's really like there are no theorems on the actual training dynamics telling you like this is actually what's going to happen. Okay, I mean that's a kind of bold statement. Of course, there are theorems out there, but I just mean like simple model problem, not like this is important in deep learning, but just as a mathematical problem, you're making a function. If I take a point from a Hilbert space, a familiar Hilbert space, what do your dynamics actually do? And so we have a pathway towards it. I think, so that's kind of the point, right? An integrable system gives you a solvable model. It gives you can look at that solvable model many ways. It gives you a pathway forward in terms of what you can do. So.
More questions? Well, it doesn't seem to be the case. So thank you.